Now we're going to meet some graphs that are so important or useful that they have a name. And the first one is the complete graph Kn. This is a simple graph with n vertices, n is at least one, and exactly one edge between each pair of distinct vertices. So Kn has n choose 2 edges, and this is the most number of edges you could have in a simple graph on n vertices. Now K1 is not very exciting, it's just an isolated vertex like this. K2 is 2 vertices joined by an edge. K3 kind of looks like a triangle. K4 is 4 vertices and 6 edges. Every vertex in K4 has degree 3, as you can see. And then, they just get more complicated from there. The cyclic graph Cn is the next thing we're going to define, a family of graphs. So here n is at least 3. And Cn has n vertices, which we label v1 up to vn. And it also has n edges, and each edge joins vj to vj plus 1, except when you get to the end, you have to wrap around to the beginning. So C3 has vertices v1, v2, v3. And the edge from v1 to v2, v2 to v3, and then back to v3, v1. All those edges are present. Okay. C4, we see 4 vertices and 4 edges, and so on. We can see that C3 is just the same as the complete graph on 3 vertices. The next family is really nice, very interesting. Family of cubes, the n cube Qn. And this is the simple graph which has a vertex for every string of bits. That's strings of zeros and ones of length n. So it has exactly 2 to the n vertices. Okay, and there's an edge between 2 vertices if and only if the corresponding sequences of bits differ only in one position. Okay. They're adjacent if they differ by just 1 bit. So Q2 is shown here. Here are the 4 bit strings of length 2, and you can check that every edge corresponds to 2 sequences which differ in just 1 bit. For example, these 2 vertices down here, these sequences differ only in the first bit, and so they're joined by an edge. And next we have Q3, which has 2 cubed, which is 8 vertices. You can see the 8 bit strings of length 3 there, and you can check that all the edges are present that should be present. And each edge corresponds to this differing in exactly 1 bit. Now what this means is every vertex has degree n, because there's exactly n positions where you could flip a bit. If you flip the first bit from this particular sequence, you go across here to the left. If you flip the second bit, you're going to go down, and if you flip the last bit, you're going to go sort of out. There's also a really nice recursive construction where you can make Qn plus 1 if you know Qn. So let's see how this works, creating Q3 from Q2. What I've done to start with is just take a copy of Q2 and label it exactly as you would in Q2. But now the trick is to take another copy, a second copy of Q2, and sort of offset it. So this is meant to be behind a little bit. At first we label it exactly the same as the original copy of Q2, like so. But now I need to make these into bit strings of length 3, not 2. So I'm going to put a 0 at the end of my first copy and a 1 at the end of my second copy. And now I really do have all 8 different bit strings of length 3 sitting there as vertices on this graph. And the only thing left to do is to join the 2 copies of each vertex of Q2 together by an edge. So going from my original copy to the second copy, and now we see Q3 again. And so we could do this recursive construction once more to create Q4 from 2 copies of Q3, and so on. Now, to introduce the next family of graphs, we need a new concept, which is the concept of a bipartite graph. And we say a graph is bipartite if its vertex set can be partitioned into 2 subsets such that every edge has an endpoint in V1 and an endpoint in V2. So the vertices fall into 2 non-empty disjoint sets, which together give you all the vertices, and every edge has to go from one side to the other. There are no edges within V1 or within V2, they all go between V1 and V2. Okay? So we can ask, is this graph shown here bipartite? Well, it's not obvious from how it's drawn, but what you can do is just grab any vertex, such as A, and start to draw the graph, seeing if you can make a vertex bipartition. So in particular, the neighbours of A, which are B and F, would have to be on the other side of the bipartition. So let's draw them on the right. Okay, now we've got B and F. And now their neighbours would have to be back on the same side as A. So their neighbours are C and E. So we can put C and E over here. C and E are actually both adjacent to both E and F. So that's sort of nice. And finally, vertex D is only adjacent to C and E, so we can safely put vertex D over on the right. And this shows that the graph is bipartite because we are able to draw it in this way that demonstrates the vertex bipartition. So we say yes, the graph is bipartite. Means 2 parts, right? Bipartite with bipartition, and you write A, C, E, B, D, F. Okay. The next example, asking whether the cycle C5 is bipartite, although we've sort of given away the answer here, it's not, but let's see why that isn't bipartite. So we'll try the same sort of argument as before. Let's put vertex A on the left, and its neighbours are B and E, so they would have to go on the right. Now B is adjacent to C, so C would have to go on the left. And E is adjacent to D, so D would have to go also on the left. But now we have a big problem with this edge from C to D, because that edge would end up completely within the left-hand side, and that's forbidden. So it's impossible to finish a vertex bipartition, and it's because the cycle has odd length. So the only cycles that you're going to see in a bipartite graph would be cycles of even length, using the same sort of idea as we used just in this example. So now we can define the complete bipartite graph, KMN. This is a simple bipartite graph which has a vertex bipartition V1 union V2, where V1 has M vertices, V2 has N vertices, and all of the possible edges from V1 to V2 are present. So this is simple and has the most possible number of edges you could have on a bipartite graph with the given bipartition. So KMN has M plus N vertices and it has MN edges. We've got a few examples here. So K12, there's one vertex in V1, 2 vertices in V2, and we just end up with these 2 edges being present. Whereas in K22, there's 2 vertices on either side, and what you end up with actually is a cycle, the cyclic graph of length 4, shown in a bipartite way. Or as the numbers get bigger, things get much more complicated.